Today, I want to dive into a brain-twisting topic that's puzzled scientists for ages, the one-way speed of light. Now, you might be wondering why we can't just measure it directly. First, when we talk about the speed of light, we often mean its two-way speed. This is the time it takes for light to travel from a source to a mirror and back to a detector. Measuring this is pretty straightforward, but what about the one-way speed, the time it takes for light to go from point A to point B without a return trip? To measure the one-way speed of light, you need two clocks, one at the source and one at the detector. The tricky part is synchronizing these clocks perfectly. Albert Einstein proposed a clever solution. He said, let's assume the speed of light is the same in all directions. This convention simplifies things and is the cornerstone of his special theory of relativity, but it's just that a convention. We can't independently verify it without already assuming it's true. You might ask, why not just transport a clock slowly from one point to another? Well, experiments have shown this method gives results consistent with Einstein's synchronization, but it still doesn't prove the one-way speed of light is isotropic or the same in every direction. It just confirms that our synchronization method works under the assumption that it is. You'd never know unless you could measure the one-way trip independently. Now let's delve into its more familiar counterpart, the two-way speed of light. The two-way speed of light is the average speed that light takes to travel from one point, such as a source, to a mirror and back again. Because the light starts and finishes in the same place, only one clock is needed to measure the total time. This makes the two-way speed of light experimentally determinable without the complications of clock synchronization schemes. Any measurement in which light follows a closed path is considered a two-way speed measurement. For instance, many tests of special relativity, such as the renowned Michelson-Morley experiment and the Kennedy-Thorndike experiment, have demonstrated within tight limits that in an inertial frame, the two-way speed of light is isotropic and independent of the closed path considered. But how do these experiments work? Isotropy experiments of the Michelson-Morley type don't use an external clock to directly measure the speed of light. Instead, they compare two internal frequencies or clocks. This is why these experiments are sometimes referred to as clock anisotropy experiments. In the October 2009 issue of the American Journal of Physics, researchers Greaves, Rodriguez, and Ruiz Camacho proposed a method to measure the one-way speed of light. Their experiment was designed to isolate the time of flight of light in a single direction, assuming that the signal return path to the measuring device has a constant delay, regardless of the endpoint of the light flight path. This approach aimed to provide a more accurate measurement of the one-way speed of light. Fast forward to June 2013, J. Finkelstein, a prominent physicist, critically analyzed the Greaves experiment and concluded that it actually measured the round-trip or two-way speed of light rather than the one-way speed. In the late 17th century, the Danish astronomer Ole Rømer made a groundbreaking discovery that would forever change our understanding of light. Rømer was studying the eclipses of Jupiter's moon Io. He noticed that the observed eclipses did not occur at regular intervals as one would expect. Instead, they seemed to vary depending on the Earth's position relative to Jupiter. After meticulous observations and calculations, Rømer proposed that these variations were due to the finite speed of light. Rømer's work provided the first quantitative estimate of the speed of light. Although it's impossible to measure the one-way speed of light independently of any clock synchronization scheme, scientists have devised clever experiments to observe changes in the one-way speed due to various factors, such as the motion of the light source. One of the earliest and most significant experiments was the de Sitter double star experiment in 1913. This experiment was later conclusively repeated in the X-ray spectrum by K. Brecher in 1977. In these experiments, the clocks can be synchronized in any convenient manner, since the focus is on measuring changes in speed rather than the absolute speed itself. Additionally, observations of radiation from distant astronomical events have shown that the one-way speed of light does not vary with frequency, indicating no vacuum dispersion of light. Similarly, studies have excluded differences in the one-way propagation between left and right-handed photons, ruling out vacuum birefringence. As we delve deeper into the mysteries of light speed, it is essential to explore theories where the one-way speed of light is not necessarily equal to the two-way speed. In 1904 and 1905, Lorentz and Poincaré proposed a theory that aimed to explain the negative result of the Michelson-Morley experiment. This theory attributed the results to the effects of motion through the ether on the lengths of physical objects and the speed at which clocks ran. According to this theory, objects would shrink along the direction of motion, and clocks would slow down due to this motion through the ether. Consequently, slowly transported clocks do not in general remain synchronized, although this effect cannot be observed directly. The equations describing this theory are known as the Lorentz transformations. In 1905, these transformations became the foundational equations of Einstein's special theory of relativity, which proposed the same results without referencing an ether. In Lorentz's theory, the one-way speed of light is principally equal to the two-way speed only in the ether frame. However, in other frames, due to the observer's motion through the ether, this equivalence does not hold. The difference between the one-way and two-way speeds of light, however, can never be observed due to the ether's effect on clocks and lengths. Therefore, the Poincaré-Einstein convention is also employed in this model, making the one-way speed of light isotropic in all frames of reference. Despite being experimentally indistinguishable from special relativity, Lorentz's theory is no longer in use.